Today, it's our great pleasure to have Georgia from Facebook AI Research. Georgia has a lot of nice works in the 3D vision domain, in particular, recently PyTorch 3D. Many of you have heard about that. And she will talk about recognized scenes and objects in all dimensions. So welcome, Georgia.
Thank you. Thank you for having me in this great seminar. I've actually watched all of the lectures so far. So it's a great effort, and thanks again for having me. So my name is Georgia, and for those of you who don't know me, I work predominantly in recognition. I like anything that has to do with recognizing objects and scenes from images and videos. And the goal here and the dream of every researcher that works in this topic is to basically create a system that is able to recognize everything from a single image. So you want to recognize the scene, the objects, the humans, their pose, their actions, their interaction with other objects, et cetera, et cetera. So take this image, for example. Some of you might have seen it before from talks of Jitendra Malik, where I stole this slide from. So here, in this case, we have an image of a street scene. And what we want a model to be able to do is to exactly recognize that. Recognize that there is 3 people in the scene that are predominantly visible. Person A is walking away. Person B is chatting and looking at person C, while person C is sitting on a bench holding an accordion, looking at person B. These are all the things that we would like for a model to recognize, things that are very trivial for the human eyes, but are not quite trivial for computer systems. And we've made some good effort in this direction over the recent years, and especially in the field of object and scene understanding, we have all these wonderful tasks and benchmarks that have allowed us to make that progress step by step every year. And these tasks are very diverse, and that's what makes it very nice and exciting. They range from understanding and recognizing objects via 2D silhouettes, or even recognizing the stuff, such as the sky, the wall, or the grass, understanding humans and their interaction with objects and their actions, or even moving a little bit further than 2D, for example, dense pose, where you're supposed to recognize a lot more dense landmarks on human bodies and now also animals. So these have kept the excitement going and have also allowed us to build systems that can actually somewhat perform these tasks. Performance is not as high as we would like it to be, but there is great progress that's being made every year on trying to reach that. But one thing that, of course, we need to point out here is that all these efforts and all these great successes are nothing else but a success story of supervised learning. We figured out how we can take a collection of image annotation pairs and transform them into a model that can emulate exactly these pairs. And this is not trivial, and I know that it's not a hot topic, supervised learning, everybody wants to move away from it, but it's actually challenging to make it work and to make it work well. So I know that this is a 3D seminar, but I'm gonna briefly talk a little bit about what it means to recognize objects and what are some of the state-of-the-art models, and more importantly, what are some of the most salient contributions in that field over in the past couple years. So when we talk about 2D object recognition, what we want to do is we want to take an input image of a real-world scene. This is a complex scene with many objects, a lot of occlusion, a lot of clutter, and any number of objects in that scene and types. And we want to build a system that is able to recognize all of these objects, despite all of these adversities like clutter and occlusion and multiple objects overlapping and so forth. So this is what the standard, the golden standard is for object recognition. And we have built models that are actually trying to do this. And I will mention Maskr CNN, not because it is the state of the art as of like today, like, October 2020, but because it has some of the most insightful contributions that have actually allowed us to build on top of it and actually carry on even today for more tasks. So masculine CNN belongs to the family of two-stage detectors. So you have the first part of the network that operates on the image level by applying a series of operations. This is the part that we call a backbone of the network. And this backbone is usually any CNN, your latest, greatest, ResNet, ResNext, DenseNet, whatever there is currently out there. The image level operations are actually followed by region-wise computations. So the backbone predicts regions that are nothing else but object candidates on the image plane. And now the region-wise network will actually take these regions and try to apply another series of computations to predict the final output. For the task of image segmentation, for instance, segmentation, this is just a sequence of convolutions, and they predict the silhouette of the object. Other tasks require different designs on this part of the network. And this is something that we'll see later on for the case of 3D. And of course, the glue that puts these two parts of the model together is this operation that we call ROI align. This operation extracts region-specific features from the backbone. And it turns out that if you're actually sloppy when you do this, then you can actually lose a lot of points in performance and will, more importantly, lead to poor quality results. So ROI align is one of the biggest contributions of masculine CNN and also subsequent models. And what it does is that it tries to preserve the image to feature alignment and even accounting for subpixel accuracy. And of course, this needs to be done in a differentiable way. And it's done like that by using sampling and bilinear interpolation. And this was the operation that replaced the formerly ROI pool that was there in the previous models, which was not actually resulting in an equivariant mapping. But the simple fix of trying to preserve image to feature alignment is basically what led performance to go from okay to now like things actually look very good. And it turns out that equally important to this maintaining image to feature alignment is training recipes. And I know the details of training are the kind of thing that actually no one wants to talk about because they're boring and they're not sexy and nobody gets excited about them. However, they can make or break your model. And we have very limited understanding of how they impact the performance. And it's very much true that if you deviate from the recipe, then your model will underperform severely. So yes, they're boring, but also they're stupidly important. And I want to emphasize that and sort of normalize talking about these things because there's a lot of junior folks that actually don't pay attention to these details. So I kind of want to bring them and resurface them. And what I want to mention here is that to achieve state-of-the-art for object recognition with masculine CNN, for example, it's really important that we need to train with large batches. And this is achieved with multi-GPU training and also large mini batches per GPU. And this is what the reason I emphasize this is because if now you want to build on top of masculine CNN, you need to make sure that anything you do for any task that you build needs to be able to accommodate large mini batches. So this is like the brief summary and that I wanted to talk about regarding 2D recognition. And now let's talk about how we can advance 2D recognition models into predicting objects in 3D. And it turns out that a lot of the things that I just talked about and the things that are important in 2D actually carry over when we move to the third dimension. So what we want to do when we want to recognize objects in 3D is we want to build recognition systems that, in addition to predicting 2D properties, now also predict 3D shape of objects. And once again, we want to overcome occlusion, clutter, a variable number of objects and types in the scene, etc. And since we had all this great expertise with 2D object recognition, we thought, okay, let's try to extend mask our CNN into predicting 3D object shapes in the form of meshes. And of course, we call this model measure CNN for this precise reason. So measure CNN takes an input image And it predicts all the 2D objects. It predicts all the objects in 2D. It predicts their bounding boxes, their object types, and also their silhouettes. And in addition to all these 2D properties, it also predicts the 3D shapes of the objects in the form of meshes. And to capture the varying topologies of object shapes, we predict and take advantage of intermediate 3D representations, in this case voxels, which are then further refined to capture the final details of the final 3D objects. So this basically allows the model to capture instance-specific object topologies with a presentation that's more flexible in this regard, and then converts them into meshes, which allows to capture the finer details. And what the model looks like operationally is shown in this figure. So as I said, we build on Maskr CNN, and this is a very compact view of Maskr CNN. And this part of the model is responsible for predicting all the 2D properties of the objects. So we extend Maskr CNN with a voxel branch whose role is to predict the voxelized object shape. And as I said, voxels are great because they can easily capture instance-specific topologies by merely predicting how to turn on and off voxel occupancies. But they're very bad at capturing fine details because they're kind of chunky and coarse. So this is where the mesh refinement branch comes in, which takes these coarse voxelized predictions and refines them with a mesh refinement branch, which learns to deform the vertices with a sequence of graph convolutions. So the output of this branch is a refined mesh of the detected object in view coordinates. And along this whole line of operations, we make sure that we always maintain the feature, the image to feature alignment. And this happens with this operation that's called vertalign, which makes sure that any feature that is attached to any vertex of the mesh actually corresponds exactly to the location in the original image. So I won't talk more about this, but I want to emphasize that this is like a beast of a model. It has all the losses that come from the 2D object network, Maskr CNN, and in addition, it has a voxel loss, a mesh loss, and a mesh regularizer. The voxel loss is nothing else but a binary cross entropy loss of voxel occupancy. Very straightforward. Defining the mesh and the mesh loss and the mesh regularizer was a little bit more tricky. Tricky in the sense that it's actually not very easy to define a mesh loss that measures the distance between two different meshes. And this is because two different meshes can actually represent the same surface. For example, you see here, you have two different simple meshes, different topologies, but they really represent the same surface. So how do you actually define a loss to compare these two? And so what we do is that we convert our meshes to point clouds by sampling on the points on the surface, on the faces of our mesh, proportional to the area of the face. And we do this for both the prediction and the ground truth. And then the loss is then a simple comparison between point clouds. And here we use a chamfer distance that I'm going to assume that most of you know, but it's basically just a distance between 2 point clouds. And we first wanted to verify that this whole pipeline of predicting voxels and then meshes and training them with our this loss and our regularizers actually works. So we use the ShapeNet dataset, which is a synthetic dataset of object CAD models. And we compare it to previous methods that were trying to do exactly the same task, but either with voxels as the 3D representations or point cloud or meshes. And we found that this actually does perform quite competitively. But more important than numbers and results were the lessons that we learned. The first lesson that we learned is that shape regularizers actually are important if the goal is to produce nicely looking meshes. But mesh regularizers, while they do produce better looking meshes, they actually lead to worse metrics because the metrics that we use to compare here, which is the chamfer distance, F1 measures, actually don't account for smoothness of a mesh. So if we actually turn the mesh regularizers off and we only use the chamfer distance as a loss of train time, then we get meshes which look very bizarre with intersecting faces, and which are not really ideal, especially if you want to use these meshes in downstream tasks, or you want to render them or do whatever else you want to do with them. But turning the mesh regularizer off allows us to improve on the aspect of smoothness of mesh, but worsens the results. The other really important lessons for us was that it is the matter of capturing object topologies is actually important. And we compare here with another previous approach called Pixel to Mesh that is a very beautiful paper with some really great ideas. And the authors there actually deformed a sphere topology. So a sphere was used as an initial template that was then learned to deform in order to capture the final shape. And as you can see here in these examples, when you're restricted to a sphere topology, you are limited in the type of shapes that you can capture. For example, it's not easy to capture holes. You can see this here in this table on the second column, where the table obviously has holes, but when you start from a sphere, it's really not easy to actually capture these holes. While a voxel prediction, intermediate voxel prediction allows you to actually capture these topologies in a more instance-specific manner. So these were the lessons that we learned from ShapeNet, but the core contribution of our method was to move to a detection setting where you want to use real input images with multiple objects, and you want to be able to detect all the objects and predict their object shapes. And for this, we used the dataset that's called Pix3D, which was collected from MIT folks and contains images of people's living rooms and other indoor scenes of IKEA objects. And our goal is to take measure CNN and apply it to these images where we need to detect objects and also their 3D shapes. And when you move to a detection setting, now of course your metrics also have to account for that. So when we measure performance on a Pix3D, we not only want to measure the box AP and mask AP, which are the typical metrics used in 2D object recognition, but we also need to extend to a 3D by introducing the mesh AP metric. I don't want to get into more details on that, but you can read more about it in the paper. So we reported these results of the Pix3D dataset, and we had two different splits. And this is the reason for that is that allowed us to study two different problems. So in the first split, which is the random split, we split the dataset randomly on a train and test set, which means that now you can actually have the same model that appears on the training set. It can only also appear on the test set, of course, under different viewpoint, under different appearance, different texture, but it's the same underlying 3D mesh. And our results here show that measure CNN is more competitive than baselines and other approaches. The more interesting results, in my view, come when we move to the second split, which is a more strict split that separates the training and the test sets so that no model on the train set appears on the test set. For example, what that means is that you might want to train for a chair, which has armchairs and kitchen chairs, but at test time, you might actually, your test image might contain like a little bar stool or whatever this is, which is very different than the shapes that you've seen for the chair on the training set. And the nice results here is that, as of course we expected, performance drops. But performance dropped not only for the 3D mesh prediction, but also for the 2D recognition for both boxes and masks. And this is a really nice result because it shows that we haven't quite figured out in the world of object recognition how to deal with novel shapes. And there is a lot more work to be done. And this is sort of what I always use as a remark when people say, oh, like, haven't we solved object detection? No, we have not. When we move to diverse and more object categories and novel shapes, we have not built systems that generalize very well. So this sort of concludes the observations from measure CNN. But before we even got to report numbers and results, to operationalize a model that was such a beast like Measure CNN, it was actually very painful. And what I mean by that is that we had a lot of engineering challenges to overcome in order to even get to the point where I can hit launch and train a model for this task. And the reason is that this humongous network that I just presented, actually a big part of it is focused only on doing 3D operations. These are operations that are different from your conv 2D or your ReLU that you're used to using when you train CNNs. These are now more complex operations. And the challenges don't even start even before that. They start with batching. So I explained to you how important it is to train models with large mini batches, especially if you want to hit good performance for object recognition. And remember that in Mascara CNN, you require something like 500 examples per batch per GPU. But batching is actually quite challenging when it comes to 3D. So batching in 2D is simple. You take your 2D grids of images, you resize them to have the same height and width, and you stack them in first dimension, you get your batch. But how on earth are we batching meshes that can have different number of vertices and different number of faces? It's not actually very clear what the best batching strategy is. So we actually had to be able to accommodate for all possible batching modes that we needed. The first, of course, and trivial one is to maintain a list of your different meshes in the batch. But lists are not very friendly for computation of deep learning operators. So instead, we can also convert the lists into a packed tensor where we basically concatenate everything into one single tensor. And for that, of course, we need to keep auxiliary tensors around to make sure to convert back to the initial list of meshes in the batch. And another version of a possible batching is padding, where you basically construct, you make sure that all of your meshes have the equal number of vertices and faces by padding them, and then you stack them on the first dimension to create your batch. And again, to emphasize that there isn't a single mode of batching that is ideal for 3D. Even within Measure CNN, even within the same forward pass, we had to convert between different batching modes to hit the efficiency that we wanted in order to be able to train the system in a time and with memory requirements that were healthy for our research. And so now that we have dealt with batching, we also needed to deal with the fact that we need to have batch 3D operators. Again, remember that we need to compute a chamfer distance, for example, among the many different 3D operators with large batches. And we can't really do this in a for loop. That will take weeks, maybe months. So we need to make them very efficient. And here I show, I will assume that you guys know what a chamfer distance is. But what is more important is that if you go and naively try to implement chamfer distance for a large mini batches, like in Measure CNN, you are hitting a performance that is prohibitive for research. Well, so this is where we had to basically go down and write our own custom CUDA chamfer distance operator to hit the efficiency that we needed. And this is only one example of the things that we needed to do in order to make this happen. There is a lot of other 3D operators in Measure CNN that require exactly the same amount of work in order to improve the efficiency of the model. And we decided that this was sort of a lot of engineering work that was done that could be useful for others. And we decided to actually package it in a project and release it. And we released it under PyTorch 3D, which is a library of reusable 3D components. And is an effort that's led by a great research engineer, Gkioxari. And of course, apart from the differentiable operators and the efficient data structures, PyTorch 3D also includes a very modular and efficient differentiable renderer for meshes, for point clouds, and soon for volumes. And so now here's where I'm stepping into 3D territory. And I'm sure that you guys know all this stuff much better than I do. But just for completeness and for people that are watching, differentiable rendering is actually very common in graphics. You take a 3D scene composed of a shape, a texture, and a camera, and you render it into the image plane. However, traditionally, this process is not differentiable at all, and recent works have attempted at making it differentiable. And let's see how, mostly for educational purposes. So rendering is composed of two steps. You have the rasterization, which computes which part of the scene affects each pixel in the image. And you have shading, which computes the color of each pixel. Now, shading is actually differentiable because it's nothing else than interpolating vertex colors or projecting face colors onto the image plane. So this is not the tricky part. The tricky part is the rasterization, which is not differentiable because of boundary issues and occlusion. Let's see why that is. Again, I'm like stepping into territory that I'm sure that you guys all know. I just want to emphasize this for completeness. So consider the pixel shown here in green, and like you can see it right here on the image plane. So if we move the blue face from left to right, then the primitive that hits that green pixel changes from the orange triangle to the blue triangle, back to the orange triangle, creating the step function that is not friendly for differentiation. Step functions are like, we hate them, right? So this is a problem that is this discontinuity because of occlusion, of boundary issues. And of course, now there is exactly the same problem that happens because of occlusions in Z, in depth, where if you take the blue face and move it from near Z to far Z, then the orange triangle comes in front of it, again, creating the step function that we hate and is not friendly for differentiation. So how we resolve this is we make the triangles transparent toward the boundary, and we blend multiple triangles per pixel. And this is something that was actually done very nicely by SoftRas, a project by Howley's lab at USC, which is exactly how they dealt with this problem. Now, the differentiable renderers in PyTorch 3D actually are very much inspired by this innovation by SoftRas, but they actually innovate in three big ways to improve efficiency and modularity. The first thing is that for every pixel, every pixel depends only on the k nearest faces. This is unlike SoftRas, where every pixel depended on all the faces that that pixel was hit by from the rasterization step. And this is important for efficiency and modularity. The second step is that we take a coarse-defined rasterization approach that actually is important for efficiency. I will not get into the details of this because it becomes very technical, but it actually allows us to make things a lot faster, to perform rasterization much faster. And the second, and in my view, one of the most important parts is that we moved a lot of the components of the rendering pipeline into PyTorch, which now allows for the pipeline to be a lot more modular and allows folks to write their own shading and their own custom blending functions. And this was unlike in SoftRas, where basically rasterization and shading was done in a huge CUDA kernel. And every time that you wanted to change that, and you actually do want to change these things, these operators, but depending on the task that you're solving, you really had to write CUDA code to do this, which is not very trivial and can lead to a lot of bugs. So in PyTorch 3D, because of all the changes that we introduced, that allowed us to actually keep the rasterization, which is the heavy load of the computation done in CUDA, and then export the outputs of the rasterizer and be able to use PyTorch operators now in order to perform the shading and the blending in order for the whole rendering to happen. And this is sort of what the pipeline looks like. So you start from your meshes and your cameras and your scene. And the rasterizer, which is now the only part of the rendering pipeline done in CUDA, is now in charge of computing what pixel is being hit by which elements of the 3D shape. And the rasterizer actually returns this fragment data that we call, that consists of the Z buffer, the 2D Euclidean distance of every face that hits that pixel in 2D, barycentric coordinates, and pix to face, and indices. So this is all the information that now one needs in order to do anything that they might want to do later on in the shading and the blending stage. This is what allows you to actually perform func shading, or growth shading, if I pronounce this correctly, or get the depth images out. Anything that you might want to do for the problem that you might want to solve is now returned by the fragment data, and you have now access to it with PyTorch code, and now you can actually very fast hack and write new operators for this. And just to an example use case, so I'm showing a little bit of code, how, for example, you would use the outputs of the fragment data to perform silhouette rendering. And now this is done basically by 2 lines of code where your distance is exactly one of the outputs of the fragment data. That is the only thing that's now needed in order to render your silhouettes on 2D plane. And of course, there's a hyperparameter sigma here that you can now choose, and which defines basically how the blur of the silhouette and the edges of the shape. So this is just a toy example of how you would actually use the output of the fragment data to perform something that is silhouette rendering. That's very standard in differentiable rendering. And of course, now that we have built this new render and we made these assumptions about the top K faces, and we have sort of modularized the approach, is question that follows is, well, does it work? And this is something that we always need to prove, that our new render actually works and it works competitively. So in order to prove that, we experimented with the problem of 3D shape prediction, but in this time, we're not going to use supervision. We're going to rely on differentiable renders to predict the shapes. So the assumptions are the same. We are going to consider an input image train time that's being given as an input to the network, and the output is a 3D shape of that object. And one thing to note here is that when you don't use 3D supervision and you want to infer 3D shapes from a single image, there's a lot of ambiguity. And the reason is that infinite 3D shapes can actually explain the same 2D image. And I'm showing an example here where we have an input image of a sphere. And this can be explained by, I show here two different shapes, but there's an infinite number of shapes that can explain it. And so to resolve and get away from this ambiguity, we assume this 2-view training setup, where basically you assume that at train time and at train time only, you also have a different view of the same object. This is a very common assumption that is done in many papers, and we sort of adopted because we want to compare to different differentiable rendering methods. So basically, this 2-view assumption at train times translates to a model that's shown here, where you have the input image, you render it, you predict the shape, you render it, you compare to the ground truth silhouette, and you also are given a second view at train time that allows you to rotate that shape, render it, and again, compare it to its second view. And this is only a train time, and at test time, we're left with our core model that takes as input, image as input, and predicts a 3D shape in view coordinates. And we use the ShapeNet data set here. Even though it's a synthetic data set, it actually, it's not the most exciting data set to work in, but it actually allows us to benchmark and compare to different methods, because the goal here again is to show you that it actually works. As an image encoder for this network, we use a ResNet 50 network, or basically it can be any CNN that you wish to use. But we try to explore more architectures for the shape network, which is basically the network that will predict the 3D shape. The first choice of a 3D shape network that we used was the Sphere FC model, which is what we baptized it, which is the most common network used in this space to predict shapes, where you take your feature output from the backbone, you flatten it, and you pass it through a bunch of an MLP, basically, and that predicts the offsets of the vertices of an initial sphere template. This is a very popular model, but I believe that you can actually do better than that by maintaining geometry properties of the inside even your model architecture. And this is where the Sphere GCN model comes in, which is inspired by mesh CNN and pixel to mesh, and uses graph convolutions instead of MLP in order to predict the offsets of the offsets up for every vertex of the sphere. And as again, this is the model which basically maintains this feature to image to feature alignment. Unlike the sphere of C model, where actually this alignment is lost. So we trained, as I said, on ShapeNet, and we chose to render at a 64x64 resolution, which is a traditional resolution used in a lot of the previous methods and papers. With the sphere of C model, we found that PyTorch 3D actually performs better. Here we're showing chamfer distance, so lower is better. And of course, the performance improves even further when you move to a more geometry-aware model, the sphere GCN model. But again, we noticed that PyTorch 3D performs better than self-res and even that model in the apple-to-apple comparison. But we always wonder why we are rendering at such a low resolution. We want to actually go higher in resolution. Resolution is very important when it comes to getting better quality outputs of a mesh. So when we increase the resolution, we found that performance improves even further for both the sphere of C and the sphere GCN models. So this is exactly where all these details actually matter about what you choose, and the recipe is, and these hyperparameters actually can make a big difference in the model. So from this exploration, we found that PyTorch 3D actually does work better or slightly better than softRes. And we also found that model that uses graph convolutions instead of an MLP actually performs much better. And that was also not only shown in numbers, but also shown in the quality of our predictions. And I'm showing here a bunch of images from the test set where you see the input image. And this is what the sphere of C model produces. And as you can see, it actually tries to predict correctly the shape of the object in a very abstract way, but it really fails on the details. So it doesn't capture all the holes in the object. It doesn't capture the right topology for the legs. This is maybe not as surprising, since this is a model that loses this alignment from the image. Now the sphere GCN model actually overcomes that and is actually able to predict these details of the objects in much better quality. And you know, I've made all this effort and talked so much about how it's important to build an efficient and modular differentiable renderer with the emphasis on efficiency. And because of the efficiency in PyTorch 3D, that allowed us to even go higher up, not only in rendering resolution, but also in the resolution of the mesh itself. So because of this efficiency, we were able to learn to deform a much larger sphere template, which now has over 2,000 vertices and over 4,000 faces, compared to the standard mesh template, which usually has less than 1,000 of vertices. And this is where we found that even that detail can lead to a much improved performance. For example, now the shapes actually capture much finer details for the objects shown in the image, like the hole off that chair. And they actually also produce a much better representation for a lot of other objects. And when it comes to numbers, we found that by pushing the efficiency and modularity of PyTorch 3D, we were able to actually even reduce the gap with the supervised methods, such as Measure CNN. Of course, it doesn't match it, but it actually has closed the gap between supervised and supervised. You can also do texture reconstruction and add texture to your output, not just to predict the 3D shape, but to predict the RGB attached to the shape. I don't want to get into the details because I have a lot more things to talk about, but I also want to emphasize the fact that we also have a differentiable renderer for point clouds. Point clouds is just a set of points in the 3D space, and now you can use exactly the same pipeline and exactly the same primitives to deform a point cloud in order to capture the shape. And that also works very well for this task of unsupervised shape prediction, and even to the extent where it's even better than meshes. And it's not surprising because in point clouds, you actually don't have to preserve any any structure with the neighboring points. Every point sort of can move independently, so you have even more degrees of freedom there. And here are some qualitative results on what it looks like to predict point clouds in this unsupervised way from input images, where I'm showing an input image and two different views of the predicted 3D shape. And of course, you can again attach texture to it and not only reproduce the shape, but also sort of the color of the object represented in the image. Okay, so this sort of concludes what I wanted to present about PyTorch 3D and why we have put so much effort into making it efficient and modular, and hopefully you'll find it useful for your research projects. And finally, in the last part of the talk, I want to move away from objects and talk about scenes and how it is important to reason in 3D at the object level, but also at the scene level. And this because 3D is not just a property of objects, it's also a property of scenes. And a scene actually changes, I just want to play this video while I talk. A scene changes with viewpoint changes in a manner that's consistent to its 3D structure and layout. There's objects in the back that move faster than objects in the front. Objects become unoccluded or occluded when the viewpoint changes. And this is exactly portraying how the 3D property of a scene actually defines the scene itself. And this is a video that I've gotten from the New York Times that shows this interactive navigation of a studio that is amazing. And it's very natural that we see this from the human eye perspective. Like our brain really nicely understands how this is all consistent. But the question now here is, how do we teach machines to do this? How do we teach machines to actually be able to nicely figure out how objects change and how the scene changes when the viewpoint changes? And I mean, this is the golden standard of what we would like our machines to do, but of course, we're not there yet. This is towards that direction. We wanted to see whether we can perform this task. This is a task of novel view synthesis, where you're given an image as input, and what you want is to teach a machine how the scene will change if the viewpoint changes. And all that the machine knows is the initial input image of the scene as it's given. And I want to emphasize that this is a task that's both, it requires reasoning in geometry, but also reasoning in the semantic space. You need to reason in geometry because you need to figure out which objects are in front, which objects are in the back, how they're going to change based on their layout. But you also need semantics in the model, because objects will become occluded or become unoccluded as the viewpoint changes, and the model needs to predict exactly how the object will appear under these changes in occlusion. And this is a chair will look different when it becomes unoccluded versus a human or versus any other object. So this is where the semantics comes in. And in this, this was an initial project or an object in this direction that I worked on for the first time ever. And this was led by our wonderful intern at the time, Olivia Wiles, and was published at CVPR. And by no means, we're not the first ones to tackle this. This has been actually, this is a very popular task, the task on novel view synthesis. And there's been a variety of methods that have tried to synthesize novel views, focusing either on synthetic objects, single object images, or using stereo or ground truth 3D supervision. So here is a summary of some of the previous works. It's not complete. There's been a lot more works recently, like NERF and NERF in the wild and all of these other fantastic papers that are not in the slide. It's a summary of some of the recent works. So our approach for this task uses a latent point cloud. And it looks like this. So you take an input image and a feature vector encodes that image and produces per pixel features. This is a regular CNN network, like a ResNet. At the same time, a depth network predicts depths for every pixel, which means that now you can actually convert your per pixel features to a 3D point cloud of points with features. this 3D point cloud is now transformed under the target viewpoint transform and is rendered in the new view. The projected features of the output of the rendering are then passed through a generator to produce the final image. And a discriminator at train time makes sure that the output actually looks natural. And of course, you at train time as well, you try to match the target predicted image to the ground truth with an L2 loss and a perceptual loss. So at train time, this method uses only image supervision. So you have the original image, you have your target view, and it also assumes that you know the relative transform between the two views. But there is no explicit 3D supervision for the scene itself. And we focus on complex scenes for this task. So we use the Matterport and replica datasets, which are scans of indoor scenes. So they come with various RGB views of the same scene. You can actually manipulate the transform, and you also have some underlying 3D information there as well, if you wish. This is sometimes for comparison reasons. So this is a great data set for that. We also use the Real Estate 10K dataset, which is a dataset of YouTube videos of walkthroughs from properties. Now, there is no 3D information in these datasets whatsoever, but they are a diverse set of scenes. It's one of my favorite datasets to work on recently. So we perform a lot of our ablations on the Matterport 3D dataset because it's a dataset that we can control much easier and perform ablations on. And we compare two methods, such as methods that actually use no 3D representation, for example, image-to-image methods, such as pix-to-pix, or we compare to a model that will, instead of a point cloud, use a voxel supervision. A voxel 3D representation. There's no supervision in 3D whatsoever for any of these methods. And we find that actually, since in our approach, using this latent 3D point cloud representation works much better. And it works much better not just in the metrics that we're showing here, but which are all about comparison of RGB images, but they also work much better when you look at qualitative results of maintaining the geometric structure of the scene itself. And here are some, are they playing? I hope they're playing. Some novel view synthesis predictions at test time on the Real Estate 10K dataset, where the input to the system is only the first view, and then through a given rotation or sequence of rotation translations, we generate the novel views. I hope the videos are playing. Okay, good, awesome. Even though we don't supervise a network with any 3D information, or do we force it to learn actually anything accurate in the any accurate point cloud representation of the scene, the model is actually able to make reasonable point cloud predictions. And it turns out that this is actually a really nice property of this model, because in order for it to actually produce novel views, it needs to make a reasonable guess about what the 3D structure of the world looks like. And this is a visualization of what the intermediate point cloud representation looks like. And I'm showing even more here. Of course, they're not accurate in the metric space. And this is expected, since we don't really, that's not really what the network cares about, but it does try to predict something reasonable, nevertheless. Another really nice property of this model is the fact that it can actually generalize very well from different scenes. So here we show how it can generalize from the Matterport dataset, which is a dataset of Matterport scans, which are of lower fidelity than a replica dataset, which is a similar pipeline, but with a much more accurate hardware design to actually capture the 3D scene. And we see that we see that the model that's trained on Matterport can actually very nicely generalize to replica, which is the more high fidelity scenes. And more importantly, the nice property of using a 3D point cloud representation versus, let's say, a voxel representation is that it can actually much easier handle resolution. And here we're showing a model that was trained to produce 256 cross 256 images. But at test time, we forced it to actually produce higher resolutions of 512 cross 512. And we see that the voxel representation actually fails in increasing that resolution because voxels are actually very tight to the resolution of the voxel itself, while a point cloud representation is much more flexible and can much easier handle the change in resolution on the image space. So there's a lot more experiments and a lot more ablations on the paper itself. So if you're interested, please go and read it. I tried to only cover some of the higher level bits and high level observations that I thought were very interesting when we were working on this project. I'm almost done, and I kind of wanted to end with a couple of conclusions when it comes to reasoning about objects and scenes in 3D. And one thing I wanted to point out is that I believe that 2D recognition and 3D recognition is actually not very different. They're actually very tight. And when we were working on Measure CNN and we were looking at the predictions of the 3D shape predictions we're making versus the performance in the 2D space, we actually found that they're very correlated. The model makes mistakes in a very similar way for both the 2D and the 3D aspect. Where the model has a hard time predicting 2D properties, it has a hard time predicting the 3D properties. So this makes me conclude that any improvement that we make in our 2D models will transfer to 3D, and vice versa. Any improvement that we can make in more accurate 3D object prediction will likely transfer to 2D. So these are not uncoupled problems. And this is maybe a motivation for people that you don't have to work on one or the other. You can actually work on both of these problems at the same time, and you will get gains probably in both. These are some observation of the mistake, exactly the point I was trying to make. And the final conclusion is, and which is sort of, that defines what I'm very excited to work on, is whether reasoning in 3D can actually lead to better representations, better features, better architecture, better models, not just for the purpose of 3D, but for any sort of task that we want to tackle. I think that Sinsin was a great example where you use a latent 3D representation to perform a 2D task at the end. But it turned out that actually having an intermediate 3D representation was the key in making it work. So maybe a 3D representation is the key to make a lot of other things work that we're not yet exploring, we're not aware of. These are my final conclusions, and this is why I'm really excited about the 3D space, because I feel that it can actually open the door for a lot of innovation in a sequence and a set of various tasks that we're tackling in computer vision. And oh my God, I've been talking for a lot of time, so thank you so much, and thank you for listening.
Okay, thank you, Georgia, for the wonderful talk. And we also have two great panelists here with us. One is Andrew from UC Berkeley, and another panelist all from NVIDIA. So we will have we have quite amount of time, extended Q&A session. So I want to start with a question from the panelists.
Okay, yeah, I have some technical question. First of all, thank you so much for a great talk. I enjoyed it a lot. And I really like your emphasis on the details and talking about because they really matter. And I really appreciate it. I think it's a really good point. I just have a technical question on this, course-defined rasterization sounded really interesting. Could you maybe give how does it work at a higher level?
Right. So it's actually a very, very technical detail, but so when you have a mesh or a point cloud, and you want to render it, there's a variable number of vertices and faces that they can, based on basically what you input to the system. So the course of fine rasterization, what it does is it tries to actually break the image into bigger tiles, and record exactly the amount of the part of the object that will hit these tiles, and that then allows the code, because of it being in a GPU and it will being parallelized, to actually then focus only on the tiles in order to make the finer rasterization. It's basically a way to. It is very inherent to how GPUs work and what is more efficient, and how to break the memory and break the computation, which is inherent to this course of fine rasterization.
I see. Great. Thank you. Very nice. We could get to a high-level questions, conversations too, but or if you had
no, this is I mean, it's like there was a lot of work put into that. So I mentioned it in like 1 second, but like it's a lot of work to figure it out.
Yeah, sounds really useful actually. Yeah.
I can imagine it also has like utilization in probably like edge devices, like mobile devices and stuff like that, where computation resources are more limited. You probably want to do those operations in parallel, right? Like on chunks of the image, instead of working on the entire image at the same time.
Right.
Yeah,
and in general, when you write CUDA code, a big part of when you design how your flow of the computation will be, it is to decide to know exactly how memory is distributed among the nodes, and how to break your problem into sub-problems to study it. And it's different than when you work on CPU. So and I'm sure that it might also be different when you work with mobile device, like when you have limited resources and how to make it work. But it's definitely part of designing something and operationalizing it.
Another thing I really like is this batch chamfer distance, because it's also really painful to implement it, and I'm really glad that, because the silhouette loss is also, you wanted to make it a bidirectional silhouette distance transform loss.
Right.
You have to do something similar, and one side is really easy to compute, but the other side is really computationally complicated to compute.
Yeah.
So yeah, this is great.
So it's hard to look at you two faces and not think about the composition of like, how do you go about doing scene understanding and incorporate dynamics? Because I think Anju's like work is very inspired by dynamic scenes, and I think most of what you've shown in this presentation is about extending from the single object to the scene level. But then my next challenge to you is like, okay, now how do we go about including and understanding dynamic objects in those scenes?
So dynamic of objects, you mean objects that change and deform, like for example, a fridge whose door opens?
That's a good example. Humans that interact with the scene is another.
Right. Yeah, I mean, these are like very hard things, because this is it's not only observational, it's also sense and touch, and which are things that we haven't quite, or I have not really, I don't know what the status is in the computational part of that. But I think that it is a very important direction to study. So figuring out how the interaction of humans and scenes of objects, and how in time all that changes I didn't really touch on that at all, but I know, I mean, Andrew is working in it, and I know a lot of other people are. So I think that's a very important direction.
So, I mean, speaking about 3D, go ahead. You wanted to ask something?
Well, yeah, no, I have no, okay, I forgot to talk about, I really, because George, okay, I'm sorry, actually, I'm moving away from the non-rigid things, because I really like the non-rigid things. So if the follow-up is on the non-rigid things, I'm happy to keep on talking about it.
It's kind of a slide of a zoom out, so you can push the non-rigid in there, but maybe you go.
Yeah, because like I really like the emphasis of the success of 2D recognition in George's talk, and I really think there's a lot that we can take away from the success, like, convolutions are good, fully convolutional things are good. And so here's a question, which is I'm teaching a class now, and I think a lot of the young kids, because of this SDF direction, like the sign distance function or the implicit function direction, where like now you're learning an MLP feature. So like the thing that I often get is like, this excitement towards hyper networks, and I think they are exciting too. I'm not saying that like, it's not, it's not gonna be fruitful. And I actually have a couple of really cool animation papers that use hyper networks and work really well. I just haven't really seen them scale up, and like it's not the way we do things in 2D recognition. So I'm curious, like Georgia, what do you think about hyper networks things and directions like that?
So I agree. So it is. So because I work in recognition predominantly, I actually, when I see something that makes sense and it works, and I'm like, yes, like I was like, that makes sense and it works. So that's a good combination. I know that there has been a lot of recent exciting work on implicit functions that don't actually in the 3D space. And to be honest with you, there has been efforts even before that excitement to actually do something like this in 2D. And the reason why you haven't seen or heard of them is because they didn't work. So, so I am very skeptical to what extent these observations will transfer to 2D. But on the same, I'm not very sure whether implicit functions and like the representation that we're using now, they cannot actually be changed in order to maintain this image feature alignment. Always the easiest thing to try is to implement something with an MLP, but I believe that it's not the next generation of these methods will actually try to maintain this. And then maybe we can rethink how can we sort of take these observations and put them into 2D and vice versa. But I do think that if we don't have humongous amount of data, if you don't have a lot of a big corpus, then image to feature alignment is important if you want to generalize. But maybe if we end up training on the billions and billions and billions of images on the internet, like that might actually go away and might not matter anymore. So long story short, I don't know, but I'm hopeful that we'll see some of these ideas transfer from one to the other.
Okay, so let's ask one or two questions from the audience, and we'll have another round of discussions among the panelists. So there's one question like, have you also assessed the scene thing for the task of monocular depth estimation, right? Estimate the depth for a single image.
Yes, so we actually have in the paper, we actually have a mention on whether if you were to make the point cloud into a depth map and how it correlates with the actual depth map of the scene. And this is something we can do on Matterport exactly because we have the depth information, and actually they do correlate. They're actually very similar. So the far things are predicted far, the near things are predicted near. So the paper actually has a lot more information on that.
Okay, thanks. So there's one more question. So is it possible to use PyTorch 3D shaders and CUDA kernels in their own project, right? So, or are we limited to use the Python API?
Oh, so somebody wants to write CUDA?
Yeah. I mean, so the question is that is it possible to use PyTorch shaders, right? You mentioned that in your talk.
We have, yeah. So we have PyTorch 3D already has implemented a bunch of the most popular shaders that you can that exist out there, like Phong, Flat, Gurode. I'm not sure if I pronounced it correctly, but so these shaders already exist. I have found that in the projects that I work on, I always write a new shader. So this is something that it's also students always don't think about the shading and the blending as being this thing. Oh, it's like part of the rendering. So whatever is a standard thing. So I encourage everybody to think about the needs of their problem and implement their own shaders based on what they need. If it's something from the traditional thing that you need and you're fine with Phong, that exists in the library, or it's not very hard even to implement. But more importantly is that you should make sure that you can actually understand what the shader and the blending function does and have a very good understanding of whether that fits your own problem. That was not what they were asking. I just wanted to point that out as like, don't be afraid to understand what shaders and blenders do, and don't be afraid to implement your own. And you can do this in PyTorch, yeah.
Okay, thank you. So I have a question I would like to have a discussion among panelists is that, so we have seen a lot of works on this kind of going from a single image, right? So using static images as, right, as the input, or basically images as a supervision signal. So there are a lot of videos, right? Do you think like how would we utilize videos, right? Because videos we can get depths, right? So so there are a lot of works on that. How if we incorporate videos in this domain? So what are your thoughts about this, like the challenges and opportunities?
Yeah, I mean, my thoughts are exactly that. I think that it's a kind of an unnatural task to ask for a system to learn from a single image to infer the 3D shape. It's not what we do as humans. That's not how we learn. So I think the video is the very natural way of learning, and is actually what a lot of my projects currently are emphasizing on, learning from videos. And it's not, again, it's not just about 3D. The same thing holds for 2D. The same, like we should be able to learn better object representations through learning through videos, even when the goal is to recognize objects in 2D. Nothing makes 3D or 2D different in that regard. The challenge with videos is the amount of data, finding diverse data sets. From what I know, there isn't an equivalent of a COCO data set for videos. And COCO here means a data set with diverse scenes, diverse amount of objects, where there's a lot of objects so that you can actually learn interactions of objects. So this is, I think, the biggest challenge of moving to video is finding the right video data sources and compute.
Yeah, I agree. I also like video a lot, and I'm moving forward. And the nice thing about video is that it gives you multi-view supervision, right? And so you can work with this. And like real estate 10K is a really nice data set, but it's also not that long. And so the baseline is not that big. And it's just being hard to get out of the wrath of ShapeNet, because it's like the moment you want to assume that there's multiple cameras, it's like you have to assume that we're going to take video of an object around. Nobody would do that, or like at least we don't really have that naturally.
It's not natural. Like you have to ask people to do that.
Yeah. And so I feel like we need a little bit more, couple of years for the commodity sensor to actually advance. And when there's 360 video translation walking around the world, I think we would be a lot better.
I agree. Yep.
So I want to follow up on.
Sorry, I just want to say that that's exactly the same issues with videos in 2D. Like all the ImageNet vid, and they basically have objects that just move in the plane. That's like not very useful.
So I think we're kind of circling around the fact that 3D is a good thing, not necessarily for the sole purpose of extracting a 3D shape, but just as a way to inform our networks about this is not just a picture of an object. This is literally a 3D object that lives in our world, right? And so if we go back to your for like Mesh RCNN is a great example, because it starts with a 2D detection. And what I would love to see, for example, is that if you introduce strictly more information, like now you have supervision not just as bounding boxes and masks, but also literally the 3D objects, the underlying 3D objects. Why are we not seeing improvements in the 2D detection stage, right? This could really be a strong result. Have this additional 3D supervision improve our 2D detectors.
I mean, this is why we started, or I started working on this in the first place. I mean, getting the 3D is cool, but I just wanted to see, can we get something more? And then the problem begins to get data. Like when you don't have a lot of data to work on, like Pix3D is a great data set, but it's tiny. So it's very hard to make any conclusions about whether you improve 2D when you are learning from very few images, or I think that it's not as a conclusive result. So I agree with you 100%. To me, that will be like the best outcome of a project like this, where you show that by predicting more, you improve like the stages even before. But I have a fear that our data is not sufficient for that.
So do you think in terms of data sets, the future is in more interactive environments like replica and similar?
Yeah, I think more interactive environments, also what Andrew just said, if we improve our sensors so that we can actually gather a lot more in the wild videos. So I don't think that we need replica. I don't think that we need this very high fidelity, like 3D scan of what the leg of the chair on the back left looks like. Like maybe that's not that important. It's important for other tasks, like no questions about that. But for learning purpose, I'm not sure that that's important. What we need is a more diversity in large scale. That's what I'm hoping. Like Coco, it's a great example. The silhouettes on the Coco dataset, when they were annotated, are really not good quality. The original Coco. Elvis, which is a subsequent dataset that tried to really improve on that. But what was important is that even though you learn from really inaccurate masks at annotation time, the predictions, because you have such large number of images, actually the predictions look better most of the time than the annotations themselves. And that is sort of like, we don't need great quality if we have large amounts of data. If we have small amounts of data, then we probably need very high quality annotations.
Talking about video, I think another thing that often we kind of leave out of the equation, but is really important when we move to video, is the role of tracking in video, because a lot of the times we kind of assume that the objects are detected or the tracklets are given to you. And I know, Georgia, you've also worked on tracking from like the 2D perspective, right? Like, yeah, what do you think about this? Yeah.
It's so hard. It's very hard. So it's a very challenging problem. I've worked on the problem of tracking for humans in 2D for these videos that have like, that are crazy in the number of people that they have. And when, and it was like, what is even happening? And you know, it's not even that you can do smart like things about appearance, because you have like a soccer field where all the soccer players from a distance kind of look the same because they all wear the same clothes. So it's like, what even are we doing? It's very hard. I think that tracking, once we move to video, it's, as you said, it's going to be this thing that we probably will have to work on if we want to utilize videos in some way.
Yeah. And then
so maybe, so maybe just getting better, like once the community is ready to introduce better video data sets, maybe this will be the time to work on all these problems.
Right, that's true, because the current tracking video data set seems like extreme kind of situation. Yeah.
But you know, speaking of other tasks but recognition, but now we're saying like tracking, for example, is a great. So we're talking a lot about this terminology. We have the scene understanding, right? But what does that mean, right? Sometimes it means a bounding box, sometimes it means a mask. Now we're talking about recovering the underlying 3D object. Do you like sorry for the slightly philosophical question, but do you imagine like what's the optimal test that we can say, okay, this is our Turing test for saying like we really understand the scene? What would that look like? What's your ideal data set and benchmark for that?
Yeah, it's a good question. And, you know, like, I think that as a community, we sort of defer from answering that. And we've instead sort of try to introduce little milestones that we think will get us to like the top. So I don't have a very good answer into what it means. I mean, I could like philosophize and start saying, oh, we should do this and that, but I don't have a concrete idea to benchmark path right now to materialize it. But I think if we're able to understand if we're able to understand all the objects, for example, which is a milestone, we even haven't hit that. I think that's a very good first start. If we're able to understand the 3D geometry, that's a very first good start. So I'm trying to look for like the trees right now rather than the forest in this particular case, because otherwise it becomes too overwhelming. Other people from like my chats with them are, oh, like any questions that you might ask the system, it should be able to answer. Like that's another way of like when they were thinking about Turing tests, like, oh, is this person on the far right, are they angry? Like, so different people have different ideas. I don't have a very concrete solution.
What about like autonomous agents like that can act in those environments?
Of course, but right. But then I don't. Do we have these autonomous agents? Like, do they exist? Like, are they? Like, what I'm trying to say is that for me, it's important to think about this, and it's important to think what kind of task can we concretely put out in the community to start for people to start sort of working on. And
okay. So I have another question for the panelists and Georgia. And so if you think about the next one data set in the 3D domain, right, for this kind of 3D recognition, of course, we have to consider like including the image inputs. So what would you, in your mind, what would be the ideal next data set that is plausible, right? Not really like out of reach, right? What would be the data set you want to have?
Is that for 3D or is that?
Yeah, for 3D, yeah.
So what I would like, if there was a data set I could say that I wish, and then somebody would deliver it to me the next day, I would like to have a Coco video data set.
Yeah, agreed.
It won't have 3D annotations, that's maybe fine. But I want this diversity because it's not just about 3D, it will allow us to study a lot more other problems. Coco video, somebody.
Video.
Okay, Andrew, you also say that you want the Coco video.
Yeah, video. Coco video, I really like. Just diversity is so important in the wild video. Because once you have the data, I don't really think it's that necessary we have 3D annotation. I agree.
How about what would be the next data set you want?
I don't know. Maybe it's my over analytic thinking, but I would imagine something that's more like a simulator based. So this, if we had like a 3D Coco stuff that you could literally play with the compositionality however you like, and I think compositionality is really key to solve many of the problems and be able to just return to the same scene but just alter a few small things. I think that's really fundamental to understanding 3D. So I would be a little bit more bold and ask this realistic staging.
I totally agree, but I actually think the simulators are actually going to be after Coco video because the world is so complex that like we can't really like define everything, and I think it's a little bit of an AI researchers kind of like ego things to think that we could. I'm trying to be more like it's not just this whole about synthesis. I'm totally for the simulators, but I think we need to mine the prior distribution of the objects and everything from real data. That's where the complexity.
It's a chicken and egg problem to some extent, right? Like, yeah.
Chisen, maybe you're muted.
So we have one more question from the audience, right? So you mentioned, so in one of your, I think it's mesh CN. So use the voxel-based representation for the 3D, right? So do you think the resolution of the voxel matters, right? Do you think could it be the very should be the coarse or fine? Like, do you think?
I mean, every time you work with voxels, you suffer from a resolution problem, and the fact that voxels are very sensitive to resolution, and so I do think that like it definitely affects the performance, so basically there is a trade-off of topology and resolution. And the hope was that you can start from a very coarse, low resolution voxel that will try to capture the topology of the object. And then the mesh refinement part will actually try to figure out how to make it finer and capture the finer objects. So there's a lot of problems that this is trying to tackle basically. And you try to use the pros of one representation and the pros of the other to fix the intermediate one. But I think that since Measure CNN, actually like a lot of people have actually tried to improve on it and work on it and to figure out other ways to do this. We also have another project that tries to get away from the voxels altogether and just predict meshes with varying topologies in a differentiable way. So nothing is set in stone, but hopefully the community will, find better ways to do this. This is the goal of every project, right? The project is like, you never solve a problem. You just put one idea out there and you're hoping that there's going to be enough traction that people will think about it more, will understand the problem more, and will improve it.
Okay, thanks, Georgia. So do we have more questions from the panelists? Andrew, do you have more questions?
Maybe since we have Georgia, and I really like the attention to the detail aspect, which is a lot of the students do need to really implement a lot of these new things. And do you have any practical advice if they had to implement some non-existing operation in PyTorch in 3D and have to parallelize this? How do you go about it, or experiences the past?
So I can tell you what we do when we develop a new feature in PyTorch 3D. And I wish Nikila was here to sort of also describe her pain, because basically it takes maybe 2 hours to implement a new feature, and it might take 3 days to implement tests. Tests to make sure that your feature is correct, that you're hitting the performance you need, analyze where the bottleneck of the performance is, and all that stuff. So of course, I'm not saying that when you work on a research project, you should do that. I don't think I ever did this much attention to detail when I was hacking around trying to get my model to work. But if that's the aspect that you really care about, then testing sort of your features, making the test cases, and understanding where performance bottlenecks are is an important aspect. And if you're really into that, I think PyTorch 3D has the tests really written up, and Nikila has done a great job creating classes so that you can test very easily and assert and benchmark your performance. So that's one. And then there is the attention to details when it comes to optimization and training networks. I feel that this is where with the students that I interact with, this is where a lot of students don't really value hyperparameter tuning because it's very boring. Of course, it sucks. But it's really important to understand how they impact the performance.
Yeah, totally. How do you actually go about? Do you have organizational things to kind of?
So I have a few things that I know. For example, one golden rule it's something that I always try to teach when I teach about that stuff, is that if you change one hyperparameter, it's very highly likely that you need to change some other hyperparameters at the same time. You can't just, if you want to decrease your learning rate, you will probably have to tune something else as well. So if you find yourself only changing one thing, then you're probably doing something wrong.
Oh, interesting. Oh, this is really interesting, because sometimes people say only change one thing because otherwise you don't know what that was contributing. So how do you actually
so this is correct when you're ablating, you want to change one thing at a time. But when you're talking about optimizing a network, for example, if you change your batch size, then and you train for the same number of iterations, then that means that you're actually now changing for a different number of epochs. So now when you're comparing to another method that trained for this number of epochs, it's no longer a fair comparison. So it needs some sort of knowledge of this stuff. Changing one thing at a time is the right thing to do when you're ablating a model and you want to understand the impact of each thing. But when it comes to tuning the hyperparameters or the batch size or the learning rate, things become a little bit more complicated.
Okay.
So when I work with students, I do encourage them to share these details with me, because I might have an input. Usually students don't want to share these details because they think they're boring. I kind of find them, I kind of like them. And I think that it's nice for them to feel comfortable to share them, because somebody else like you or somebody else in the meeting room might know something about it, might advise them to change something.
Okay, you have the last question.
Oh, wow. I'm actually, so I think I wanted to ask something more about this implementation, because what kind of interests me is usually I tend to think of hyperparameters as something that you kind of try to squeeze out more juice of your model once everything is kind of roughly works. But did you ever encounter a situation where the hyperparameter was a make or break point, where, the learning rate scheduling, that's something I usually keep for last. Did you ever notice a project where this was if we hadn't done that early on, the project would never
Right. I think
just want more.
right. So yeah, I think that is very correct. That usually it is you try to choose try to get as many points as you can from tuning. And so for some projects, actually, a 2 or 3 point difference can actually lead you to publish or not publish, right? So there's that aspect of it. Our other methods, like I'm also very sure, and I don't know how this will sound, but I'm sure that a lot of the papers that are being published that are based on performance and, oh, I improved this by this much, it might be the case that if you tune the other thing more, you would have actually have gained the same number of points. But there is actually projects, especially in the large scale learning sort of field. For example, the ImageNet in 1 hour paper, this is where hyperparameter tuning breaks it or makes it. And it's not about squeezing 1 or 2 points, it's about does it work or not. Yeah, I mean, it's to the discretion of the problem. It's not all problems care about getting the best numbers, of course, but because deep learning is such a complicated concept actually, and we don't quite understand it quite well, it is important to sort of try to understand how your model varies or changes with hyperparameters. Another example is batch norm, like such a big mystery, right? So it's really not that complicated what it actually does.
Right.
Yeah.
Awesome. I love your motivation. This is like always listening to you, like really boosts me up. Like I want to go and code like hands-on like crazy now, you know.
Oh, okay, well.
Tune my hyperparameters.
Okay.
I'm happy that's what you got out of this hyperparameter. No, I think it's important. I'm glad. I want to normalize it. I want us to talk about hyperparameters.
No, I like, yeah, it's a good point. Bring it up to the discussion level, not just keep something hidden in the appendix.
Right.
Yeah. Okay. Thanks for the wonderful seminar and the Q&A discussion. I think is I've enjoyed a lot. I believe the audience also enjoyed a lot, and I thanks all for the attending. Okay.
Hi, thank you for having me.
Thank you, Georgia. See you.
Thanks, Georgia.
Bye.
Great talk.
Bye bye.